Guys on YouTube, can you hear me? All right.
Your last, if they're funny, they're like jokes, kind of like I am conduit for nuts, or like I refuse to tolerate lactose.
You got the- Oh, really?
Yeah, I was looking around because I wanted like.
No, I like the game. Really nice.
Can you put some pizza emoji in the chat? So that's for
I told them,
emoji.
guys, you missed the pizza. Can you hear me?
It's a lot of things.
A lot of things. All right, be ready. We will take the picture now. Please enable your camera. Do some zoom. You missed a lot of things. Maybe we can point the camera to where. Oh, the pizza's already gone.
There is some crust left.
Now the entire room's looking at you. All right, be ready.
I'm hoping not everybody like.
Just 2-3 minutes. Yeah. Promise.
Just summarize.
Yeah. Promise. All right. I will present quickly. Just. All right, guys. So hopefully everyone can hear us on YouTube and Zoom. Yeah, you can keep eating. I'm going to share just a few slides with you. These formalities just for ending the semester. So as we promised in the first lecture, who remembers what is the goal of the course? All right. Yeah, that's cool. So the first thing, which is the most important one, increasing awareness about existing directions in computer architecture, especially the advanced direction, including processing and memory, near memory, and so on. And the other goal, do you know how many hours do we spend offline preparing for all those presentations? 10 hours. Can you imagine? 10 hours. 10 hours. Can you guess the number? What was the longest mock presentation ever? How long? Oh, you have to include them. 2 hours. 2 hours?
For us, 2 hours.
It was 2 hours.
3 hours. 3 hours? People in Zoom, you can still participate. How long was the longest mock presentation? Almost there.
Presentation.
We literally stayed for 4 hours fixing issues and giving feedback. How many times the maximum time we repeat the same mock presentation?
0.
No, 3, I would fail the student, simply. I would fail them. 2 times. Luckily, 2 times. Okay. But I believe what I saw, especially from today, people did great job transforming the mock presentation into a real presentation. Okay. Yeah, they deserve it. And that's true basically for everyone. So it was extremely rare that I didn't give feedback such that most of the slides need to be changed into something else. Okay. And that's something great, meaning that at least you are learning, you are willing to learn, you are willing to improve yourself. Please keep using the exact same rigorousness throughout your life. Whenever you want to prepare a presentation, please keep the same thing you learn over here in whatever presentation, whether it's short, long, keep doing that, right? So we are live streaming, we are recording, we have all the material on YouTube, on our website, the slides and everything. I hope this will be a valuable resource for everyone. So feel free to share it among your colleague. We have the other course that we provided last semester, Advanced on Bioinformatics. Next semester, we're going to teach computer architecture for undergrad and master student only, right? So again, it will be another new course. We receive a lot of positive feedback on YouTube, so feel free to add your own feedback, whatever it is about the course in general. Remember, there is a way to say thank you at GSU, which is sending special letter to one instructor, I think, per semester. I'm not sure about the eligibility condition, all this stuff. Check it yourself and then decide. This is one of the ways to say thank you. The other way, to evaluate me or rate my professors. I have no rating at all, okay? I'm sure you'll burn it. The other one, this we have to announce in the classroom, GSU evaluation. I think it's already open. I'm not sure when it will be closed, maybe in 1 week or 2 weeks, but it will be very soon. So better to do it today, tomorrow, at most within the weekend, okay? This is extremely helpful for everyone, for me and for yourself as well. Remember, based on the feedback that I received from the previous semester, we decided to keep these mock presentations. All right, whoever took the course with me last semester, there was no mock presentation. You handle it yourself. And the mock presentation was a result of honest feedback that I received, okay? So everything you say, I'll take it seriously and I'll try to improve for next semester. This is my record. It never happened, even in Switzerland. The average rate that I was taking about 4.2 out of 5, okay? But the number of students were much larger than what we have in Switzerland. Switzerland, like 17, 22, something like that. Over here, we have about 50 students, which is great. If you remember the story, I was allowed to only take 27 students in this course. I get like 60 requests to enroll in the course. It was amazing that GSU accepted to extend the capacity. We went for 40, and then we extended a little bit to 47, but we couldn't take everyone. There's the room capacity. There's a lot of restriction on the hazard, on the all those stuff, right? But luckily, we took like 50 students, which is something great to have. I would expect to keep the same rating or so. So let's see what we will have. And I'll share it with you maybe in the next semester. Just some of the feedback that we received. You already have them in the first lecture. So feel free to write whatever you like. One downside of this course, I believe that we exceeded the time, most of the presentation. I did my best to keep within the limit, but I asked you several times whether I should cut off the presentation and stop it with a hard limit. And most of you said, we like to keep it going. It's up to you. You are presenting, so you should control that. You want to exceed the time to 8 o'clock. But that is, I think, something I want to improve next semester, for sure. Would like to thank Sapar. I think he did a great job. He was maintaining all the stuff. I know it's a headache, 50 students, everyone sending, I don't know, email, I have headache, I don't want to attend, and all this stuff. So Sapar is handling that. So thank you so much, Sapar. You were a great TA. And good news, we received a grant recently within the last 2 weeks, and I'm hiring 4 master's students for the next semester, this semester, starting from January, right? It's not PhD, it's a master's student. We will have the opening soon on the website so you can apply formally. I will give priority to those who were volunteering in the lab, and let's see how it goes. So the promise is that the fund will go for 1 year, including the summer. So we will pay those master students even in the summer. More details, you'll find it on the website, but feel free to send me in advance your CV, things like that. The topic is more into LLM combined with bioinformatics, especially on fine tuning and stuff like that. Quantization, optimization, all of this. All right. It was a great meeting all of you. I would be very sad that most of you graduating this semester, but this is something great for you, meaning that we will have the opportunity to meet. Maybe we could invite you if you are working in a company or something, we will be in touch. But we have PhD opportunities as well, so consider that. Thank you so much, guys. Don't want to take too much time. Let's jump into the other presentation. All right. Pointer, yeah. I can use the one in the middle. And there are markers.
போட்டு விடுங்க கையை பசிருக்கலாரோ அதுதான் சரி கை ஃபுல்லா ஈரம் start or okay keep here. Can you start or can we start? So good evening all. Welcome to the last lecture of the course. Sorry, presentation. Yeah. So myself Nikitha and my teammates Shrinidhi and Pradeepta. So we'll be presenting about the paper Decoupling Camera Sampling from Processing to Avoid Redundant Computations in the Vision Pipeline. So it's a micro 2023 paper. So let's just begin with a real world scenario here. So I guess most of you would have come across this robot in our campus. So anyone can guess how many cameras it has? Any numbers? Yeah, it has about 6 to 12 cameras. While comparing this with the paper, like if you imagine it basically what it does is it avoids the obstacles and it delivers the food. So that's what it does. And then another example we could take is this autonomous car. So here the camera will continuously record the environment, like the buildings, car, red lights, and the trees. So even when the conditions don't change, let's say for example here the red signal, for several seconds the red signal will remain the same. So the system keeps processing every frame again and again to detect the exact same information here. So in these both scenarios, the world doesn't change fast, but the camera frames changes. So that's what we'll be discussing about in this paper. Uh, so if you imagine if you are in an autonomous driving, every 100 milliseconds, the system needs to react to what it sees. So if it is even a fine delay, it will be like a difference of stopping the car or hitting an obstacle. It will cause more issues. And then when it comes to AR or VR, even the slightest delay of the movement or any network latency kind of things can cause issues. So the system needs to be extremely fast and also smooth to process it. And when it comes to mobile or battery powered systems, we we need it to be working under strict power and real-time limitations. So the key issue here is the computer vision reacts at the speed of camera, not the scene change speed. So here regarding the continuous vision systems capturing high FPS, high resolution images where most frames will look more identical. Yet the processor will keep processing the same frames again and again. So it will lead mostly to wasted compute or memory waste or and also the energy waste. So this inefficiency will be speaking about in the paper. So how it answers it. We here referred few related works. So the first paper is the frame exit, conditional early exiting for efficient video recognition. So the key idea of this paper is like how it learns when to exit early in a video recognition models, so that simple frames require less computation while the complex frames get full processing. So the results this paper gives is it reduces the processed frames by 30 to 50% and also reduces the model compute only, and also helps in saving the memory bandwidth. The second paper is efficient one-stage video object detection by exploiting temporal consistency. So here the key idea of this paper is that it reuses the temporal consistency across frames to reduce redundant feature computations in one-stage video object detectors. So the results this paper gives is that it improves and boosts accuracy by 2 to 3 AP, and also it optimizes only the detector offering no reduction in ISP, memory transfers, and region level redundancy. So the third paper is energy efficient and real-time computer vision with intelligent skipping via reconfigurable CMOS image sensors. So here the key idea is a reconfigurable CMOS image sensor which selectively skips reading unimportant pixel patches, and the results it gives is that it saves the sensor level energy but only at pixel and or patch granularity, and there is no front end back end coordination and also no reuse map and no integration into the ISP pipeline here. We'll be seeing all these in the Delta paper. So here we'll see what the paper answers. So the key idea of delta is like it skips the redundant regions before they ever reach the heavy processing stages. That is like if the frame is same, it doesn't need to be processed again and again. It can just catch where the changes are, and then it will process it. So that's what delta does. And next is the frame exit, the paper that we talked about before. So it stops processing late in the pipeline. So after a lot of memory traffic and computation has already happened, it says, the paper says that, and then delta in opposite way, it says that the workload from even entering the pipeline, like before it enters the pipeline itself, it will recognize what are all the changes in the frames. So another advantage is that it filters region by region, and then it uses a backend kind of approach as well. And delta uses brief signatures also. Uh, so here we'll see about the executive summary. So vision frames contain heavy redundancy. So consecutive frames, like it will be, as I mentioned, it will be always similar. So traditional systems will still process the every frame fully each time. So this will lead to like waste of computation and memory traffic and energy. So here delta addresses this by detecting the temporal similarity early in the pipeline. And next is the uh, it it also uses the backend for cached computations. And like as I mentioned before, it will be using a brief signatures, which we'll be seeing in further slides in detail. And also it reduces wasted processing. And it and the latency is also improved by 15% here. And the energy is reduced by and energy reduces by 17%. And here the accuracy has no compromise. So yeah, the key ideas shared in this paper is that consecutive frames in continuous vision are often highly redundant. Only small parts of the scene usually change from one frame to the next. And next is the detect similarity inside ISP. So this will be the earliest stage in the vision pipeline. So by doing this comparison, the system can avoid the unnecessary data that needs to be sent to the backend. And next is the brief descriptors. So this will be like lightweight and fast and robust. And then it sends only the changed regions, so instead of full frame. And then it also reuses the cached features for unchanged regions. And a threshold, we use two control mechanisms here. One is threshold and next is the masking. So for threshold, when the system tune it how aggressively to reuse the regions, and then mask, this will ensure the certain critical regions like object of interest. And the key results shared in this paper is the latency is dropped by 15%. So and also the energy is reduced by 17%. And as I mentioned before, the accuracy has not compromised here. And also the backend workload is significantly decreases, and the memory traffic is reduced greatly. Uh, this is the main topic of this paper, delta. So which means don't look twice, it's all right. So what basically the idea is that if the scene hasn't changed, we no need to again process the frame pixel by pixel. So it can be used from the cached memory itself. So like it's a similarity aware vision front end for eliminating redundant processing. And also the key idea is that it enables the camera and the image signal processing to detect the regions of the image, and then it will process it. So like I mentioned before, it will be only processing only the unchanged, I mean only the changed regions, not the unchanged ones. To have a look in the front-end technical architecture, firstly, so the frame will be divided into regions. So, and then the brief signature comes into the picture. So it will be taking per region, and then we'll be comparing the previous frames also by using the Hamming distance. And then the changed frames will be going to the frame buffer, and the unchanged ones will be reused again. And here we have a zero latency overhead in the worst case. Okay, so for those who write down.
To begin with, okay. I have a sore throat, so please mind that. Long story short, basically we are considering driverless cars like Waymo, and we are just saying that in such systems where we are taking pictures very regularly, there's a lot of computation that is being involved. For every picture that you take, there's a computation. For every picture that you take, there's a computation. So that is kind of causing a computational overhead. So how can we reduce that? So that's the gist of this paper. So the first question arises, is there actually a need to reduce the computation, or is there actually a computational overhead? So for that, I have four main reasons. The first one being this. Here you can see in the first two pictures, there is a slight change in the angle, but you might be like, is there any change? You can probably see there's a tree here. There's not a tree. So it's basically the car has moved forward. Here there's slight change in the position or the angle, but still the camera is capturing that change. So that's one reason. Second, there's what if there's a slight change in the pixel values? For suppose there's very less sunlight and at one instance, and then probably after 10 seconds or so, the sun comes out, and then you have a proper sunlight. So there's not much of a change, like when it comes to the road. There's no another car that's coming in front of you, or there's not much of a change. It's just the surroundings that are changing. But does that require extra computation to be done is the question. So here you can see there's redundant there's redundant pictures that being taken. So it's just a small distance that the car is moving, and still it's computing. So that's called computational overhead. In the second case, it's just like sun came out, and then again you're recomputing everything. So this is one scenario where you can say that yes, computation is a little redundant here. So you can just skip it. In the next slide. So this is the second case where I can say that yes, computation is not required. So here you can see, just concentrate on the smaller bricks or the smaller blocks down towards the picture. Here you can see when we consider smaller areas, 60% here, it is according to the paper, they have found out that 60% of the regions are identical. So if you consider a smaller region, most of the area is identical. But if you consider the whole picture or the bigger picture, it is not identical, because see, from here, you've moved to here. So definitely the viewpoint changes a little. So definitely the pictures are not identical. But if you check just for a smaller region, then there is more of it's like more identical. So what we can say is that if we consider smaller regions, then it's more identical. But if at all we consider bigger regions, it is not identical. And that's the reason why computer thinks that there's a significant change. But in reality, there's not much of a significant change. It's just moved out a little, move ahead a little on the road. So that's second reason. Next slide. The third, or probably the more convincing reason is that here you can see that there are a lot of regions that are repeating. For suppose the trees, the sky, these are all repeating. So do they require computing again? Like, does the system require to need to compute everything again and then decide, okay, whether it needs to take a left or a right? It does not, right? It just needs to take into consideration those areas where there is a significant change. Whereas the sky, the trees and all, they can be omitted. So here you can see there are two stable regions. One being the yellow region, that is sky, road, trees, etc., that can be actually omitted from the computation. And the blue regions, where this is just a parallax error. Parallax, I'm pretty sure everyone knows, but for those who don't know, it's basically like if at all you move a step ahead, you find the object to be a little nearer to you. For suppose that chair, it is to some distance, and now when I move a little ahead, it is a little nearer. So that's basically a parallax error. So we are considering those, and those do not require you to make the computation again. The system does not need to take those features into computation. Only thing is that if there is a significant change in the frames, that is when the computation needs to be done. So that's the whole idea. Next. So this is the fourth reason why I can say that computation is required. Like computation is not required for all of the frames. Go to again. Sorry. So temporal gradient. This is basically telling you that the difference between the frames. So sorry for that. So for suppose just for 1 minute, you're clicking like 100 frames. There's higher frames per frames per second that is being taken. Then there's lower temporal gradient. By that I mean, so if there are more frames that are being taken within a short duration, the change is very little. For suppose I'm taking 10 frames from here to here, there's very less change. But when I'm taking 10 frames from here to here, there's a significant change. From here to here, the position of the car might change, right? So if at all there are high frames per second, and if there are frequent frames that are being taken within a short duration, then it is kind of creating redundant frames and you don't require computation again. So if at all there is less frames per, or yes, if at all there are less frames per second, then you can see the significant change in the frames. Then you can say that yes, computation is required. So basically the whole idea is to reduce the computation in driverless cars. You can take that example. That's the best example we can give actually. So these are the four main reasons I can say to support the answer that yes, you don't need to compute for each and every frame that a car is capturing, camera of the car is capturing. The next part will be continued by Shrinidhi.
Yeah, so I just want someone to tell what does the term decoupling mean? It's just a normal English term, but like what does decoupling mean? Do anyone know? Yeah, perfect. Yeah. So decoupling means separating, and camera sampling. So we're going to see how the camera sampling are segregated based on whether it is changed or not changed. Yeah. So this paper delta, it's like a novel solution which actually avoids the redundant computation in vision pipelines. So as Pradeepta told, not every frame needs to be recomputed because some regions stay the same and some region doesn't change. And for regions that changes, we are going to compute a brief signature and we're going to see how it is done. So this idea, the paper actually proposes this delta idea, which actually processes only the changing regions and not the, it doesn't process the full frames. It is also compatible with all the CPU, GPU, and ASIC backends as well. and it mainly focuses on ISP. As you like, a person who is more into camera and photographing might know what is ISP is. So ISP is actually one of the uh, thing which is there in the camera. It's called as image signal processing. So it is there inside the camera. It is between. It acts as a intermediate between the camera and the backend. So it actually focuses on the modern ISP front ends, and which is controlled via the backend software. And it also enables the dynamic trade-offs between the energy, latency, and accuracy. So here, for decoupling, we're going to see which are the components here, which are like 3 components. First is camera. So camera is the one which captures the entire frame. And ISP, as we talked about before, it actually processes the raw image, and it converts the image into a raw image into a full scale image, which is like seen, like it actually converts the pixel image into an image where humans can see. And it can also filter out the unchanged region and the changed regions. So the backend actually receives the image data for further processing and computing. So we're going to see what the traditional method is and what this paper has actually provided. So in the traditional, this is the traditional method. So as you can see, the camera, so this is the one which captures the full frame. And let's say this is before that, let me explain what that is. Like, so let's say this is an image, right? So this image is called as a frame in the paper. And that if this is an image, let's say they are like dividing each image into grid. They're dividing each image into grid, and this one small box is called as region. So this is as one. This is IR1. So this is like one region in a total frame. This will be called as IR2. So as it goes on, this will be called as IRN. So there'll be a lot of regions based on the size of the image. And the grid size is actually, you can take the grid size as anything. But the default one is 31 cross 31. But it can be either 3 cross 4, or even smaller range or bigger range. It doesn't matter. So yeah. So as I was saying, the camera actually captures the whole image. And this is the image, as we saw here. This is the image. This actually sends the whole image to ISP. And I have colored these regions as red. So let's say the red regions are the region which has actually changed from the original image. So this image is actually sent to ISP. And ISP is a pipeline which actually, in the traditional pipeline, what it does is that if it gets an image, it actually changes the color, it changes, it sharpens the image, it does all the work so that in the backend, all the process will be easier. So it will make the photo even more clear and sharpens it. And as you can see in the traditional method, the whole image is sent to the backend. So it doesn't filter out the changed or the unchanged region. So it actually sends the whole image. So the computing power and the energy time is actually wasting here. So full frame processing, backend must process all the regions. So in the current δLTA method, they are actually introducing the data filter in the ISP region. So where the camera, it takes a photo, it sends to the ISP. And the same here, the red regions are the regions where it has marked as it has changed. Actually, we'll be also seeing how it actually categorizes if a particular region is changed or not changed. We'll be seeing in the future. And this whole frame is sent to the ISP. And since it has a δLTA filter, what the δLTA filter does is that filter actually segregates the unchanged and changed. So it will actually, we'll see that how it does later. And after it filters, only the changed region, that is only the red color changed regions are sent to the backend. So the backend will only process the changed region. And for all the unchanged region, it will actually take the older cached memory from the older photo. Oh, it's okay. This is an example. Can anyone just see what it is and just give a vague idea of what it is? Like, what you understand from seeing that photo?
New headline.
Yeah, and also what's the expression of the person. Yeah, yeah, perfect. So let's say you get some news, right? Let's say one celebrity is marrying someone else, right? And you read all the tabloid stories. And when you're reading, you might find many articles which repeat the content again and again, and you feel so frustrated reading the same content again and again because it's very boring, right? And at one point, you'll feel frustrated like him, and you'll be like, okay, I'll just stop reading and I'll just move on to something else. So this is what happens when you compute one thing again and again, which is like waste of energy and time. And with delta filter, what it does is that it will actually highlight which part has alone changed. So if you read an article or something, if it says like paragraph has changed or something, if you read that, it'll be easier for you to read, and it'll save time and energy. So let's see why decoupling is needed. Yeah, so traditional pipelines. As we saw, traditional pipeline, it processes all the camera frames, and because of that, the computation is high, and also there is energy and time wastage. And the redundant regions, which are like repeating again and again, are transferred, and in the traditional method, it's processed continuously, all the regions in a photo. So because of that, again, the computation is high. And next is the front end. The front end cannot adapt to what backend needs. Because the front end, it doesn't segregate the change unchanged. It actually repeats the same process again and again, and totally it's a waste of computation power. And delta actually breaks this coupling. So it actually sends only the distinctive regions to the backend, and it also provides front-end and back-end collaboration. We'll see how the back-end actually controls the front-end. In the traditional method, back-end doesn't control the front-end, but in delta, it actually controls. So what delta really does, right? So this is a small diagram which we can explain the whole process. So as I said, this is the camera. Everything starts from here. So it actually captures a frame and it sends to the ISP. And the ISP has a signature buffer and delta unit. So the signature buffer is where like, for example, these are the regions, right? So for every region, it will calculate a signature, brief signature, and those signatures are all binary. So they'll be stored in the signature buffer. And for every region, for IR1, IR2, it'll be calculating the brief descriptors, and it'll be storing signature buffer. And that's what the delta unit does. The delta unit is where it will actually calculate the brief descriptors, and it actually compares it with the threshold and the Hamming distance. And after it compares, it actually directly sends to the CPU. Threshold and mask is one of the components which will be in the backend, which will be explained further by my teammate. And reuse info is where, for example, if this region is the same as the previous region, then it will ask the backend to actually reuse the info from the previous image so that it doesn't have to compute again and again. Frame buffer is where, for example, if this is one frame, it actually processes the whole frame, and it stores the frame. In the meantime, before it goes to the backend, it actually stores the frame in the frame buffer, and the backend will fetch the frame from the frame buffer. Yeah. So it optimizes the end-to-end image transmission processing, and the ISP filters. As I said, the ISP actually filters the region using the brief descriptors. The brief descriptors will be stored in this signature buffer, and the backend process only changed region reuses the cache result for others. So the backend, as I said, if a region doesn't change, it actually takes the info from this reuse info, and it will use the same info again and again. And proactive interface allows backend to control. So as we said, the proactive interface. So this is how the backend actually controls the front end, using the sorry, using the threshold and the mask. So the threshold is a similarity, sensitivity, and mask is for causing the critical regions to always transmit. That will be further explained by my teammate. And by following this process, it actually achieves the latency, energy, and also even though delta is introduced, the accuracy for the traditional as well as for delta remains the same. So front-end operation, let's see how delta works here. So let's say, as we said, this is the frame. So we divide the frames into the grid regions. Here we have taken example 3x4, but you can take any grid example, that's okay. And we actually extract the brief descriptors. So for each region, the brief descriptors are calculated, and the brief descriptors are actually compared with the current frame signatures. So let's say this is the second image that we get, all right? And let's say another image is that this is the first image. So this is the first image that you send to the ISP. So it will calculate the the buffer brief descriptors for all the region, and it will store in the signature buffer. And when the second image comes, it will calculate brief descriptors for every region, and it will compare. For example, if it's like this, so it will compare the brief descriptors of this one and this one. And if it's similar, then it means the region is not changed. So if the region is not changed, it won't send it to the backend. So that's how that's how the paper actually helps reducing the computation power. So as we see, the current frame signatures, yeah. Yeah, yeah.
The threshold value can be either static or it can be dynamic, where in the computer actually detects if there is much of if there is error, then it kind of increases the threshold value. Otherwise, it can be either static or dynamic.
Yeah. Based on the hardware design, it will actually change. But the default is 31 cross 31. But based on the default size, it can be any region. Yeah. Yeah, so as we said, we compare the brief descriptors of both the frames. And if it's similar, we'll discard because it is the same region. And if it's this thing, then we'll send to the frame buffer. And from frame buffer, it will go to the CPU. And change region identifiers, it actually, whatever regions are changed will be stored in the reuse information for backend for further processing. And it also operates in parallel. So ISP, the thing is that when I said ISP actually does color changes and sharpening of an image, right? So as that process continues, the delta process also continues parallelly. So it doesn't wait for another process to happen. So as it does parallelly, the time saved, and it actually doesn't affect any, it doesn't create any impact.
No, but when you look at both the images and you're doing the frame difference between them,
Yeah.
and you're only storing the differential pixel. Now you're losing the actual object that has now introduced in the new scene.
Yeah, it's because the older one, I mean, if for example, if these both are same, you won't send this region to the backend, right? So the backend will know that this region is actually the same as this one. So whatever feature it calculated before in the before image, it will directly take it from there. So for whatever regions it's changed, it will recompute the features in the backend. So it doesn't waste the time.
Entire image being processed.
Yeah, in traditional, the whole image like gets processed, but in Delta, it doesn't do that. Yeah. But if the Yeah, but since the frame per second is like very high, so per second there'll be a lot of frames which are captured by the camera. So a lot of images will be kind of similar. Yeah, depends on speed and everything. Yeah.
It does not consider time, Professor, but if there is a significant, basically, like I'll be talking about it later, but there is a change in the pixel value. For suppose if it's turning from blue to complete dark green, then there is a significant change in the pixel value. So that is being accounted. The change in the pixel values are being accumulated, and then it is then compared with the threshold value. And if there is a significant change, like threshold decides if it's a significant change or not. If it's a significant change, then yes, it will be recomputed. Otherwise, the similar regions will be discarded, and then changes will be.
Yeah, so let's see how the backend controls the front end. So as we said before, in the traditional, the backend doesn't play a role with ISP at all, but here it plays a role. So what it does is that the backend actually sends the threshold and the mask value to the front end. So she'll be explaining about threshold and mask even more better. I'll just give a brief idea. So the threshold is what defines as how similar both the regions are. And the mask is ensures that an important region, even though a particular region does not change, but if that region is like very important and critical, then it will send that, even though it doesn't change, it sends that region to the backend. So it also enables the dynamic adjustment, like it finally reduces the latency, it saves energy, and also the maintain the accuracy similar to the traditional as well as to the current method. And the front end informs the backend about the change region. So only then the front end backend will know which regions are changed, and it enables the proactive optimization. Yeah, so here, as I said, the same thing I explained here, same thing. So this is the first photo. And so the IR, as I said, is the nth region in the ISP, the nth region. And FR is the nth region in the frame buffer. This is the frame buffer, as I said, this will store the frame. And B is the brief function, where the brief signature is like calculated, and actually compares the brief signature using the Hamming distance, which we'll be seeing later. So this is a frame. This is frame 0, this is frame 1, and this is frame 2. So here, both the frames are actually compared. So as you can see, IR0, here the brief signature is calculated and goes to the next region. And finally, all for the whole frame, the brief signature is calculated. This is the first image. So it actually full image is gone to the frame buffer. And this is a frame 1. So here you can see, again, it actually calculates the frame buffer, brief signature for every region. And it actually, this image is compared to this one. And as you can see, the orange ones have changed, have changed. Like these orange regions have alone changed. So that's why these orange alone will be sent to the backend. And these blue will be actually, these blue regions will have particular, what to say? So these blue regions will have features which are already being calculated by the backend. So those features will be directly extracted from the older image, and it will be used here. For the orange, it will compute again. And this is a frame 2. So this is another frame which comes in, and again, all the brief signatures are calculated. And these green are the changed regions. So again, for these green regions alone, it will calculate. And for the other blue and red, it will take from the older frame. Yeah, so as I said, it actually, ISP, actually, the delta and ISP collate together parallelly. So it will happen everything at the same time. And it performs brief extraction, matching without slowing the frame processing. And let's say worst case scenario. Can you guys tell me what will be the most worst case scenario?
All regions have changed.
Yeah, same. All regions have changed, or maybe the delta is like kind of disabled. Yeah, so if that is like the worst case, it will go back to the traditional. So nothing is going to happen, but it's going to compute again. So nothing is going to stop. So it handles worst case scenario as well. And it ensures that the real-time performance are done in dynamic video as well. So the goal for this is low latency, energy efficient filtering for the redundant regions.
Moving more into technical, like how is it actually going to do it? How is it going to differentiate how whether the regions have changed or not? So there comes into picture B, binary robust. So in brief, it's called. So basically, this is to know whether there is it is to basically to summarize the intensity pattern or change between the regions. And for this, we are taking a fixed pair of pixels. That is what here we are taking A1, B1, and so on.
Who? Sorry.
So yes, so while computing for the brief, first we taken the n fixed number of pixel pairs, and then we perform a binary test, wherein we check if the intensity is less or if there is any change in the intensity of the pixels or not. If there is a change, then yes, otherwise it's a no. So it's basically if it's a blue and it's a blue again, then it's going to be a 0. There's not much change. Otherwise, it's going to be a 1. And then we concatenate the result into an n-bit vector that is called as a brief signature. This is basically a concatenation, zeros and ones. And we are making it simple for the computer because it's just binary and it's very easy to compute. So that's the reason why we are trying to introduce it into the system, because it makes it much more faster. It's actually very easier and faster for computational purposes. So what do we do with binary brief signature? We compare the regions using the Hamming distance. So brief signature actually tells you whether there is a change in the intensity of the pixel or not. 0 if there is no change, 1 if there is a change. So that we are concatenating and creating a brief signature. And that we are again checking it if there is any significant change in the regions or not. That we are using a simple formula, that is Hamming distance. And then we just check it with the threshold. If the Hamming distance, if there is a significant change, then the Hamming distance is going to be greater than the threshold value. And then we can say that there is a significant change in the frames. Otherwise, if the Hamming distance is less than the threshold, then we can tell that the regions are similar. So that's how we are checking if the regions are similar or not. So more about the brief descriptors will be told about my friend.
So here we'll see why we are using brief descriptors more in detail. So robustness for delta. So like the changes will be happening more of between the consecutive frames. So it will be like more of a small changes in the like the noise or the illumination kind of things. So it will be taking very. And the next thing is the no need for scale or a rotation invariance. So, and also delta is more of a hardware friendly. So it will be performing simple binary intensity comparisons. So as like mentioned before, it will be using a Hamming distance, which is like XOR and also the pop count. So here we'll not be not using a more of floating points of ops like SIFT or surf. So because it will be more of cost and also more complex. And next is the compact representations. So we'll be using here a signature buffer size that will be less than 4% of the image size. For example, if we take a full HD frame, HD frame, and then in delta it will be more of like a smaller version, like approx 64 KB only. In full HD frame it will be of 2 MB. So in this slide we'll be seeing the correlation with a temporal gradient. Here, the observations made in this paper is using Kitty sequence 00 data set. So in this, there is a strong negative correlation between the normalized TG and brief detected similarities. And the values are like 10 FPS in the sense it's like minus 0.7, and if it is 30 FPS, it's like minus 0.8. So the interpretation this as said in this paper is like if there is a lower motion, more brief similarity, and the more regions are reused, and it validates the brief's ability to capture spatiotemporal redundancy. So this is the delta unit architecture. So here, firstly, the process will be beginning with the camera input. Like here, it will be streaming the 2D line buffer, which is of 32 cross 32 window size. And then the window will provide the local neighborhood needed to compute the brief descriptor. So then from this window, the hardware will use the comparator bank. Here it will be performing the binary intensity comparisons, and then the generated signature for the current region will be shown in the format of BI of n, and then it will be compared to the stored signature for the same region from the previous frame. And next, delta will be computing the Hamming distance between the two signatures. If the distance is below a configurable threshold, the system outputs a reusable signal. So meaning that the region hasn't changed, so enough to require reprocessing. And then if the region is considered unchanged, the backend will simply reuse the cached computation. If the region is changed, the microarchitecture updates the corresponding entry in the signature buffer. Yeah, this time. Here, as mentioned in the paper, it is like this only static. So here we'll be seeing the delta ISP. So in this pipeline, firstly, the camera interface feeds the raw sensor data, and then it will be followed by the demosaic color correction, and then the sharpening thing, and then the DMA transfer to the SOC, and then the delta will be happening, the delta similarity filtering will be happening. And then when the region is unchanged, the catched catched image will be reused again. And here for static or low motion scenes, like 30 to 50% of reduction in ISP workload will be happening. And then when it comes to 64 KB signature buffer, it's like very low memory overhead, and there is zero additional latency happening here. And also this system level reduces the memory bandwidth, power consumption, and also the CPU and GPU processing load.
Okay, so the brief signature and all, they were all in the front end. So now let's talk about the back end. So can anyone summarize what happens in the front end?
I think we look at images, and if they are similar, we don't send that to a processing device. We send signature, right?
Yes, exactly. So now the front end, it actually checks whether the regions are similar or not. If it's similar, it does not send. If it's not similar, then it sends the brief signature to the backend. So that's exactly what happens in the front end. And now coming to the backend, backend basically receives the frame buffer, that is the change regions, and the reuse information. Backend basically makes use of two main components, or two main values, I can say. That is the threshold and the mask. We'll talk about that in the further slides. So this is basically, it tells you, it kind of, to summarize, I could say that the first frame, or as soon as we start the car, the first frame that comes into picture is actually the new region. So all of the region in that frame will be considered. So that's what is being written here. So the frame 0, the front end sends all of the regions because all of the image is new. And then it is being, the features are being extracted, and it stores in the cache. For the next frame, that is when the actual computation or the brief or the delta comes into picture. Here we actually mark, as Shrinidhi already mentioned, we check if the regions are changed or reused, and then the changed regions are being sent to the backend. The same happens for the consecutive, like the next set of frames as well. So at the back end, what it does, for the change regions, it actually does the feature extractions and then decides basically whether to take a left turn or the right turn, and then the computation actually works. But if at all it's a reuse region, then it does not actually take that into consideration. So in that way, we are actually making it more optimized. Next slide. So effective outcome, the backend operates as if every frame is fully processed, but actually it's not fully processing each of the frame. It's just taking into consideration the changes that have happened in the frames. Now, as I already told, that backend mainly takes into consideration two components: the threshold and the mask. Threshold actually decides whether the regions are similar or not. It is a deciding factor or the deciding value. So lower the threshold, it is stricter similarity. So there are fewer reused regions. And if there's higher threshold, it means that more regions are similar. And since this is a deciding factor, this can be either a like static value, we can either have a static threshold value, or we can have a dynamic or an application aware the threshold value. This is basically like it uses its own computation to decide whether there are errors, or if there are much errors, and then it actually kind of changes the threshold value accordingly. So it is like, if the tracking quality drops, the backend can lower the threshold value and can make the regions as not similar and take the regions into computation. Basically saying that it's probably incorrectly taking important regions as non-important. So that's how the application can be more dynamic in deciding the threshold value. And delta actually pitches in for an adaptable threshold value, because it helps in better accuracy, latency, and even is more efficient when it comes to energy. Now, the second component in the backend is the masking. As Shrinidhi already discussed, there are a couple of critical regions that need to be considered whether or not they are changed or unchanged. For suppose when it comes to pedestrians, roads, road borders, they are important regions. You cannot ignore whether they are changing from one frame or the other. whether there is significant change or not, you need to know the boundary of the road, right? So those are critical regions and those need to be considered. So that is where we take into consideration masking. That actually is done. We mark the regions as one. If at all, we say that it needs to be sent to the backend because it is a critical region. For suppose pedestrians, cars, or various other objects of interest. Or but if at all the feature is not important, for suppose a bird or a sky or trees, then those can be for those regions we can then use the brief signature to check if there is any significant change or not. So that is where masking and threshold comes into picture. Next slide. Special use cases for masking is that first, because for the frame 0, that is when the card starts, the first frame that comes in, the whole of the frame is important, so the whole of the frame is sent, so you mask all of the regions for that frame. And for the subsequent frames, it is just the selective regions, for suppose the pedestrians or the traffic signal lights, etc. Evaluation methodologies and etc. will be continued by my friend.
So, so now we saw how the delta fully works, but now let's see how they have, how the authors of the paper have actually evaluated the delta. So here, this is a setup that they did. Yeah, so the first setup was they actually mimicked the whole pipeline using with Gem 5. And also they have customized the whole ISP device, which is very similar to the frame buffer behavior. And they have used DRAM Sim3, which actually models the main memory. And they've used the backend CPU, which is the off-the-shelf Gem 5 CPU model. And they've also mimicked and the next simulation they did was they actually inputted the video sequence, which are analyzed to generate the reuse information. And in the simulation, they actually they wanted to see how the setup actually calculates the brief descriptors, which are the binary value. And the hardware modeling they did was first they actually they created the delta similarity filtering stage, which are modeled in the cycle accurate RTL, and they ran it with parallel to the ISP. So there were no pipeline stalls because it ran parallelly. And the ISP stream they used were like two cross 5 stencils and two 2D line buffers. And the workload, they use the Kitty dataset. I think it's a very famous dataset. Do anyone know what is Kitty dataset? It's one of the most famous datasets. Huh? No. It's very, I mean, it's the whole topic. Like, we explain the whole paper, right? You can kind of correlate. Like, what is the input for? Yeah, correct. So it actually has all the image, video data set, which are captured while driving. So they use the Kitty data set. And let's see how the system, how they compare the systems and the power modeling. First, they use the ORB SLAM 3 version where they set the baseline. So they actually use 3 versions to compare. So the baseline is the traditional method where it actually uses the original ORB SLAM. And the software catching is another version where they actually calculate the brief signatures for all the region, as we said, but they did not segregate the unchanged and changed. They actually sent all the regions to the backend. And the delta is where they did the same, the brief signatures, but they sent only the similar regions. So to avoid the extra memory access. So in the further slides, we'll see how the output actually differs from baseline, software catching, and delta. So for checking the accuracy, they actually use the EVO tool, which is like a trajectory tool, which we'll see further how the result of the whole delta is. And next is the power in area, where they use the delta unit, which is Synopsys 14 nm, and they use a signature buffer CACT. The memory, as we said, the main memory they've used as DRAM infantry, and the CPU they use MECPAT scale to 14 nm. And for the baseline, for the traditional, they use ISP 700 megahertz, 150 megawatt, and 10 millisecond latency. For CPU, they have used the ARM 64-bit and 3 gigahertz. For memory, they used L1 32 KB, L2 1 MB, main 8 GB, DDR3. Yeah, so here we'll actually see how the delta improves the latency and the like we'll see how the delta actually classifies the similar regions here. So as you can see, they have set static. For here, they do not use the dynamic threshold. For testing, they actually use the static threshold. So they've used the thresholds 1.0, 0.9, 0.8, and till 0.5, they use these static thresholds. And they have actually found out that for lesser thresholds, the similarity is high. It's because for lesser thresholds, like what to say, for lesser threshold, the sharpness was more high. The clarity for the lesser threshold was more high. That because of that, the regions in each frame were easily compared between the older frame and the newer frame. So for lesser thresholds, the sharpness was high, and for higher thresholds, sharpness was low. So because of that, the similarity differed. And here you can see they have also drawn a graph for the threshold and the maximum APE. So here you can see that for lesser threshold, the error was not that much big, but there was only like a slight error. So most of the similar regions are detected at the lower threshold, and the accuracy actually remains stable until aggressive threshold. And only a tiny AP increase was found at the higher threshold. And similarity threshold controls the reuse effectiveness. Yeah, so here we'll see the slide. This slide actually shows how delta actually improves the latency and the energy compared to the two baselines. So as we said, this red is the baseline. So it's the traditional model. The gray part, the grays are all the software software only cache, where I said before that in software only cache, they actually calculate the brief signatures, but they send all the regions to the backend. For the green, which is the delta, they calculate the brief signatures, but they only send the change regions to the backend. So here you can see that in the average latency graph, you can see in the average latency graph at the top, here actually delta consistently shows the lowest latency. That's because it actually avoids unnecessary computation for unchanged regions. And for the tail latency comparison, here tail latency is actually which measures the worst case scenario delays. And actually delta improves the performance significantly here as well, as you can see the green line. And this is important for like the real-time systems where the occasional long delays can be very dangerous. And for energy comparison, yeah, so for the energy comparison, you can see that the delta again consumes the least energy here. So the software caching actually increases the CPU overhead, as well as it sometimes hurts the energy efficiency a bit. So, but while delta avoids that by operating inside the ISP. So here we'll see the cost of the hardware and the efficiency. So here the delta units added were like minimal area, which was 0.12 millimeter square, and the signature buffer stored, the memory was like 64 kilobyte, and the 2D line buffer, as we said, the 32 cross 32, it was around 60 kilobyte, and it also supported the parallel ISP processing. So the overall power was like 50 milliwatt, mostly from the 2D line buffer. So this slide shows how delta actually behaves as we increase the camera's frame rate. Here, as you can see in the left graph, we see that the region similarity increases with the FPS, right? So as the FPS increases, the region similarity also increases. At higher frame rates, like 40, 60 frames per second, the consecutive frames are even more similar. So meaning that delta can reuse all those regions again. And in the right graph, you can see that we compare the computation cost with the camera frame per second. So here, the baseline actually grows. The baseline is the blue line and the green is the delta line. So you can see that the baseline actually grows linearly with FPS. So like more frames are like computed, but delta's workload is like nearly flat. So because of that, delta only processes, this is because delta only processes the changed regions. So the workload is also less. So we actually wanted to try implementing this. So yeah, the thing is that we tried searching a lot, but there was no public GitHub repository, unfortunately. So we couldn't try. And also they did not release the modifications as well. So we couldn't mimic the structure, but yeah. No, everything was private. Like they did not release anything public. Yeah, so let's now see the strengths. So the first strength is the ISP level optimization. So as we said, the delta actually removes the redundant region of before frame buffer write. So it actually helps cutting the compute as well as the memory bandwidth. The next is a low hardware cost. As we said before, the hardware cost was relatively low. It actually requires only a small signature buffer and a lightweight Hamming comparison logic with 50 watts overhead. And it is also applicable to any vision pipeline that uses the region-based processing. For example, we just said talked about SNAP, but it can be used in feature extraction as well. It also improves the efficiency without any accuracy loss. So as we saw before, there was no accuracy loss at all. Just it improved the efficiency. So the smart reuse thresholds prevent the trajectory accuracy while reducing the end-to-end latency and energy as well. And configurable interface, the backend can specify, as we said, the backend actually sends the threshold and mask to the front end. So it enables adaptive or task-aware behavior.
We'll be now seeing about the weaknesses. So threshold sensitivity. So its aggressive reuse thresholds may skip important small changes, which might cause slight AT accuracy degradation here, and region granularity issues. So fine details inside a region may change but still be marked as similar, which may limit its effectiveness in real-time world. So limited evaluation scope. So experiments are mainly on ORB, SLAM, and Kitty data set. So it's not tested on fast moving drones and all. Here. Next is the reduced benefit during fast motion. So when the camera movement is rapid, it reduces the interframe similarity. So which will cause the lower use and which will again lead to smaller grains. So the key takeaways from this paper is that so delta is a hardware and software co-design. So this will reduce the redundant CV processing without changing the SLAM algorithms, and it's also effective for smooth motion scenarios where temporal redundancy is high. And also it provides 15.22% latency reduction and 17% energy savings, and it gives a minimal hardware overhead. And also it can complement other techniques like feature catching, adaptive sampling, or hardware accelerators. And here delta shows the importance of the ISP front end and also not only the back end. So the future directions are like adaptive thresholding. So it might dynamically adjust similarity thresholds using the scene motion or the backend confidence, and learning based similarity detection, where it can replace brief with more robust learned or lightweight ML based descriptors. And next is the hierarchical region splitting. So it can use variable sized regions. So it will better capture small local changes as well. And next is the support more vision tasks. So it extends delta to object detection, optical flow, and semantic segmentation. Next is the hardware prototype or ASIC implementation. So implement delta on FPGA or ASIC to validate real world latency and energy gains.
Yeah, so we have some questions. First question will be a very easy question. You want to start with an easy one.
So
What is the
what is the full form of
I can't
delta
find a
here?
more easier question than the full form of delta. Not the difference. I just want to go and talk.
It was
Yeah,
it was mentioned in the slide.
I think the third or fourth.
Any guesses? It's don't look twice. It's all.
So it means like not to
You
look at the
yeah.
unchanged region again. Yeah. So the next question is like, how does delta differ from the previous software-based catching approach? Anyone? Okay. Okay, it's because who answered? It's because in software.
You can try.
Yeah. So it's because in software we calculate the brief signature, but we send the whole full frame. But in the delta, we don't send the full frame. Yeah. So why is brief suitable for delta's hardware implementation? Sorry, Prof. Second. Yeah, we are sending the full frame from camera to ISP and to the backend. The delta is actually kind of a technique which will be enabled parallelly with ISP. So the software itself is delta, but it will be ISP is a hardware, so it will be enabled. The software thing will be enabled in the hardware ISP. Yeah. Yeah. So okay, why is brief suitable for delta's hardware implementation? Anyone?
You said you.
I think it's because I guess it's because of the third presentation and after the party. I guess it's fine. Yeah. Yeah, as we said, brief uses the binary operation. It operates with zeros and ones, and it is actually XOR press pop count. And it's very hardware friendly, so that's why they've used the brief. Next. Yeah. So what is the purpose of mask? I think it comes in backend. So what is the purpose of mask? I'll give an example maybe. Huh?
Follow the road lines and also pedestrians.
Perfect. Yeah. Correct.
I can remember that.
Okay. Yeah. You connected with the example. Good. So this is the last question. This is the last question. So how does the delta maintain accuracy even by skipping some regions? Okay, I'll say. It's because it uses a catch feature. So so the similarity threshold is actually tuned based on only visually stable regions are used. So importance changes are still directed. Don't have any question? This was actually presented in 2023. And
The papers that we saw recent papers, they are using like ML techniques as well now. It's like 2024 paper. So yeah,
but
nothing
they
much.
haven't talked about the delta. Yeah. Yeah, so here they haven't used ML at all. So that paper did not meet the limitations of this paper. So what they did is that they just wanted to implement ML instead of brief here. So instead of brief, they actually implemented ML. Yeah. Yeah.
Honestly, here.
1 hour, 15 minutes.
So thank you so much, guys. Any questions on them? All right, so for the grade, I almost have them ready for everyone. I need to check the annotated version of the paper. Based on that, I will drop some grades, increase maybe. Probably by Monday, I will send you a draft of grades. If there's any issue, I'm happy to discuss them. You can just send me email and discuss them. I'm happy to provide some feedback. I already record some feedback on my notes based on each one performance. Remember, those grades are individual, not group based. I think we have until December 18 or 8.
19th of December.
Oh, that's a lot. That's a lot. No, I think we will be finalizing them by next week or so. Okay. Yeah, but please be careful. You have to check with me right away once you get the grade. Okay. Otherwise, it will be difficult to correct. Hey, yeah, I'll check it. I have good mind. You and Neil. I think, both of you send me something. Okay. Email me either Sunday or Monday. Neil, have you?
Oh, chocolate.
So you didn't do any progress. I don't know your performance. And then yeah, we'll have to Sunday or Monday. Yeah. And both of them, I will have discussion with Neil and Ash, I think. All right. Yeah. All right, everyone. Tomorrow morning.